So I'm not going to go long. In fact, I hope to end early and go super fast, and I'm going to talk really fast. I invite you to yell at me during the actual talk, because that will be interesting, because I have a lot of really silly, opinionated things, and I'm really curious to see what you think. So I've done a lot of things. You guys have all done a lot of things. Solar cars, satellites, rockets, medical equipment, except stuff like that. The one thing the talk I actually want to give is this one, which is we have an entirely open source CubeSat kit that we pioneered at Portland State University that's built on KiCad. And so it is, just going through it, there we go. You might notice the purple-ash park boards. That's the 1U CubeSat right there. That's the Onshape model for it. And we have a 1 through 3U, and everything was designed by undergraduates, which means everything catches fire and everything is terrible. And we've gone through a bunch of different revs. We have a back plane, and we have all these different things, and blah, 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 blah. Wouldn't that be a cool talk? Yeah, nope. All right, so who works on open source projects? All right, this is for you. I am sick of your stuff, and you need to shape up. I've been in industry for a long time, and then I started working as a senior instructor, which I've really enjoyed, but one of the problems is that I have to teach students KiCad. And then I have to work with these industry capstone projects when they're seniors with all of these, mostly open source kinds of things. And so I have students who are trying desperately to use open source projects like Arduinos or whatever. And I have to deal with, like that was last quarter. These are all different. Some of these have circuit boards. Some of these are proto boards. Some of them are really cute. Like they have little LED lights. This is a dice that you roll and charges on a little base station. There's some music stuff. These are all KiCad projects. And all of the schematics are garbage. Capstones. So what I hope to do today is just talk about schematics and talk about all of you working with me to make your schematics better so that when my students use your stuff and when I contribute to the open source and when you come to our open source, we have some, what's the right way, beautiful schematics, useful schematics, schematics that we can look at and use right away. Okay. So you all know that it's a schematic, nodes, and nets, and you have a net list, right? We all know that. We all use KiCad. So there you go. Yeah? I mean, we're done, right? So just to push this a little further, who knows about Skittle? Yeah. So Skittle is hilarious. It's Python code that makes your schematic. So screw your schematic. Yeah, no, So, okay, but why? Why do we use visual schematics? Well, because you've got 4 billion years of eyeballs behind you. And yes, you can see tigers in the grass really fast, but you can see other things really fast. And so that's why we use schematics. It's a visual language. You ready? What was that? You took one look at it and someone said that was a LED and a resistor and that's it. You didn't even have 100 milliseconds and yet you saw that and you parsed it, right? So you ready? So that was impressive. Let's try it again. You ready? I'm gonna go slower this time. What was that? Come on guys, what was that? You guys are electrical engineers. Come on, let's go. It's a voltage divider. So this is why schematics matter, which in less than 100 milliseconds, you could parse a voltage divider with a capacitor filter, but you could not make heads or tails of that. So I want blink-like comprehension times on our visual schematics, because a good schematic should standardize, simplify, modularize, and communicate function, all in a blink of an eye. So I want to go back and talk about stealing stuff from other people. So if you've not yet read The Visual Display of Quantitative Information, thank you, from Edward Tufte, you need to go pick up a copy. I'm sure there's free PDFs on the web, but it's actually a beautiful book. And it's really about graphic design. It's about the fact that white space is the most powerful separator. Yes, we'd like to put things in boxes, but boxes are visual noise. We have too much junk, and the more white space we use, the faster we can see stuff. Visual flow. When you read a schematic, your eyeballs go certain ways. Are you actually taking that into account when you lay out your schematics? And there's meaning where you put stuff. In architecture, and the dang computer science people stole this from them too, we have this idea of the design pattern, an easily understandable modular repeating pattern. So for us, it's not necessarily a function call or a binary sort or whatever. We have these ideas of the voltage divider, of the follower, of the inverter, right? These are things that we should be using, and we should be building these design patterns so that you can blink at something and understand what's going on. So if you remember the Stranger in a Strange Land, the idea of grokking, right? Understanding what's going on in a blink. That's what we want to get to. All right, so what's that? Yeah, it's differential, right? Yeah, it's that.
With a horrible TI.
Yes, yes. Shh, don't say it. All right. So the point is that this is a perfectly valid schematic, but it's not useful. It's not a design pattern. It doesn't allow us to see what's going on in the blink of an eye and see if it's correct or not. So that's where I want to get to. I want to get to something that communicates data and power flow, is simple and clear, and obsessively well labeled. Now, if you just do schematics for yourself, I don't care about you. You can do whatever you want to do. The only people I care about are the people who are going to actually publish their schematics, and we're going to read them, right? So I'm going to say some controversial stuff. If you just make schematics for yourselves, you don't get to respond to me. But if you publish stuff and you disagree, I want to hear. Okay. So the first thing is that stuff flows left to right. So thank you. So inputs on the left, outputs on the right. If you can. It never actually works like this in practice, but you should try that, right? And if you can't do that, you should follow a path. And you should follow a path that has enough white space to actually let your eye follow the path of the data or the power, right? So here's an example. It's not a great example, but you can see we have a radio chip right here. And you can kind of see that you can see little arrows right there. So you're kind of going through here, going through there. There's an output over here. So you've got your inputs to the radio over here. It's bidirectional, so everything's kind of messed up and everything. But it's at least you can track it with your eyes. The second thing is stop it with the power symbols. Grounds point down, negative supplies point down, and positive supplies point up, always. Please don't do that. Another thing is, this is really, really lazy of us. A lot of us use the actual physical packages of the part as the schematic symbol. Do not do that. Yeah. And the reason for that is because that's useless, right? It doesn't tell you anything about the actual electrical connections. What we want is this. We want to know where the power and the ground is. We want to know where the inputs and the outputs are, where we connect the crystals. This is just useless. That's what the layout is for, literally the layout, right? So occasionally I'm wrong. And sometimes the actual schematic is the layout, but it's very RF-y and very weird. That almost never happens. Use white space. So right now we tend to put all of our little circuits in boxes and things like that, and that's fine, but that's not as good as using white space. If you have a really tight schematic, use boxes. You want to be able to group things so that the person who's reading your schematic know that those symbols are together. Please label the blocks. I think I'm missing a slide. Hold on. No, I'm not. The other thing is, please minimize the number of sheets. On the other hand, don't minimize the number of sheets. Don't be Olemex. I love Olemex. There is no reason that you need to fit all of this on one page. We are not printing this out anymore, right? So the idea is let's use the minimum number, but at least let's group things like the power supply and the connector and things, right? So we always use 11 by 17 sheets because we're not going to print it out, but it's up to you. And if you're running out of white space, just add a sheet, right? Group, but don't make me page through 8 different sheets for no reason. Block diagrams are super great on your root page, and now we can actually make block diagrams that matter. So with hierarchical blocks, so this is an actual root page. It's a battery charger module. You've got external power coming in into a charge controller that goes out to the host system. You've got a cell interface down here, thermistors down here, and a microcontroller that controls all of it. And this is a block diagram. It's not a great block diagram, but it's a block diagram, and it's part of the schematic. I think that's really cool. And I look forward to seeing how far we can push this so that our block diagrams become useful. In general, please use wires and not labels for connections. And this goes back to the visual nature of schematics, which is I can see that this is connected to that in way less time than I can find where VN USB is around this. And yes, I can hit Control F, but now I've just lost 20 seconds hitting Control F and zooming around to find it, where it took less than 100 milliseconds for me to just see that this was connected to that. So when you can, use wires. You can label your wires. We love labels, right? But use wires when you can. Sometimes you can't, right? It's off sheet, or it would be really awkward to run like, this one label, one wire all the way around. That's fine. That's what global labels are for. Please do use labels. They're really helpful. And that's just because you can just reference them. Again, we're gonna look at this flow, but wouldn't it be nice if that was a label down there as well, just so we could see exactly, and then we could match it up and just do double checking, right? All really, really quickly. In general, please don't do this. Don't use labels for off-sheet labels or labels that jump across between symbols. And the reason for that is that's text. I can't tell what that is. That could be anything, right? That's a global label. That's a label that's going somewhere. So please do that. Also, please turn on the sheet references, the intersheet references. You can go to schematic setup, blah, 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 blah. And now I know that those two things are going to sheet 1 or sheet 5. And I can jump around, and I know sheet 1 is the connectors. It goes off to the connectors. So I immediately know that without having to look it up. Please use actually useful power supply names. VCC is not useful. VUSB is very useful. 5 volts might be useful, but VUSB might be even better, because who knows who's actually read the USB spec? Yeah. You know what's going on here, right? USB is 4.5 to 5.5 volts. It's not 5.0 volts. It's not guaranteed. The other thing is try and use the sort of standard engineering paradigms, right? So we've got min, typical, max, right? So here's my USB voltage. It's typically 5.0, but can be minimum 4.5 to maximum 5.5. And I'm typically pulling 35 milliamps, and at the most I can pull 500 milliamps. That statement right there is so much more information than 5V, right? That actually gives you actionable information. Even just having a text comment that says a 1 amp supply, right? That already tells you a lot about what's going on in this circuit. So here we go. We've got V-bus. It's 9 to 19 volts. Oh my God. Okay, I'm really glad I know that, right? V-bus is not useful, but 19 volts is useful. And that goes off to 3.3 volts at 2 amps max. Okay. Right? Those are clues. Those are clues so we don't make fire eventually. Undergraduates love fires. All right. Please use the text feature. Use all the text features. You guys are artists. You are circuit artists. Please continue the artistic tradition by marking up your boards. For example, tell us what we should expect at test points. That would be nice. The other thing is, when stuff is weird, please leave us a note. Pins 11, 12, 13, 21 are intentionally left floating. Pin 9 and 10 are both inputs and are intentionally shorted. WTF? That's okay, but that's fine. I said it, so now you're like, okay, so that really is a thing. All right, that's fine. I've called out. Now I don't necessarily have to go look, because I've told you this weird thing is right there. Also, you see that right there? Look at that. That's telling us which way our RF is flowing in this bidirectional radio. That's really useful, because now I can trace this out and I can see what part of it is the receiver, what part is the transmitter. And that's just a little arrow, right? These kinds of clues are really important to the person reading your schematic. Okay, I have to show you this because this is literally the worst schematic I've ever seen. It's so bad that it's kind of good. So this is the evaluation board for the MAX 2769, which is a SDR GPS system. So they literally did everything wrong. I'm so proud of them. I think it was a grad student at Maxim. All right, so check it out. First of all, what they did wrong, they made it a package, right? That's not useful. Then, actually, you want to see something fun? I think I have it open. There, that's the same chip, right? You can see the digital inputs over here, the RF inputs over here, the digital output over here, which the power supplies are. Now, here's really fun. Where are the power supplies? Okay, where's VCCIF? Is it right there? Yeah, it's a net label. That's exactly right, because that's ground, right? It's bypass to ground. Those are bypass caps. So we have to go look at VCCIF. So now instead of knowing where VCCIF is or what the voltage is, I now have to look up VCC. Sorry, I'm just taking you down this horror. Oh, there it is. Oh, but it goes to VCCA. Okay. So I'm going to look for VCCA. There it goes, there it goes, there it goes. It goes all over the place. Oh, okay. It's a MAX 8510. It's a 2. Oh, they don't even tell me what the voltage is. I happen to know it's 2.85 volts. Right? But now I have to go look up that sheet, and that data sheet, and I have to go find out it's a 2.85 volt. I've just wasted 5 minutes trying to understand something that should be absolutely trivial. What I should be trying to understand is all the weird RF magic going on, right? But no, instead I'm dealing with this damn schematic. So, and it actually just gets worse. I love this thing. So this is kind of fun. This is an old style tech Series 422. And what I just love about this is it's got it tells you stuff. This is the oscillation frequency thing. It's hard to tell on the screen, but that's a little image of the scope output. So that you know when you look right there at 0.5 microseconds per division, that's what your scope should look like when you probe it. That's so cool. And it's really nicely laid out. And I would tell them, hey, you guys, instead of using 0 volts, you need to use ground symbols and things like that. But it is beautiful, and it was hand-drawn, so I forgive them. All right, schematic checklist. Make sure your power is distributed through supply symbols. All supplies point the right way. Important nets are descriptively named. All these things, right? So I have linked to this an actual checklist, and I invite you to grab it. At the end, I'll give you a QR code so you can get directly access to this. And what I'd love to know is I'd love to have you guys look at this and add comments. Comments are turned on. And let me know what I missed, right? There are some things on here that are really more almost like ERCs, like MOSFETs oriented correctly with respect to the body diode. Who's done that wrong? Oh, come on. There's more than you than are doing that. That kind of thing, right? Make sure you've got your bypass capacitors. Designed for fail, group components and separate modules, power supplies, that kind of thing, right? So this is a checklist that I've run through several hundred undergraduate students to good success. And I would really love your feedback on what I'm missing here and what you would do different.
Two wires crossing with a junction, though. It's my pet peeve.
You want to go around it, or what are you saying?
Never let a crisscross happen.
Yeah.
No more than 3 connections in the junction.
Oh, no more than 3. Yeah, okay. Oh, okay. That's good. See?
Are you leaping over, or did you forget to put the circle?
Right. Well, that's up to you. Good. That's it. I wanted to be really fast, so I just cruised through this. That's the thing. Please go ahead and grab this. That links you to this Google Slides, and then from there you can get access to the link to the checklist. And also, it's got my contact information on it. I'd love to hear from you. Anything that you can tell me about what your pet peeves are for schematics and for this kind of open source thing so that we can understand each other better, I would love to hear. And then eventually we're starting a website and we'll probably start posting these rules and try and kind of get it out there a little bit more. And I'll post that in a KiCad forum or something like that eventually when that happens. Anyway, that's it.
Anyone have any questions?
Oh, I thought they were going to be. It's going to be dangerous.
I love this, and I really appreciate what you're doing. And I'm curious, just because this was one of my pet peeves, and Eli and I were just joking about it too. People need to freaking read and understand IEEE 315. You can download it from a million places. For free. It's been around since the 70s, but it standardizes every electronic and electrical symbol for use on schematics, and everything has a purpose and a reason for existing, including the circle on a transistor.
It's like a tuxedo.
If the transistor is in a discrete package,
Yeah.
the circle indicates it is in a discrete package. It has a meaning, and it must be used, and people
Fascinating.
freaking leave it out all the time. It
All the
pisses me
time.
off.
Just
I
a
love
quick
this.
note. KiCad does not endorse pirating IEEE 315. You can purchase it at the IEEE website and support IEEE. They're a wonderful organization. Thank you.
Yeah, I'll get it. That's great. I didn't actually even know that existed. This is great. What was it? Crossed wires, no more than 3, right? This is great.
So, right here, on the. So I noticed you briefly talked about block diagram schematics,
Yeah.
but you also use a lot of global labels everywhere. So
Yeah.
where do you draw the line between hierarchical and global?
Oh, I don't draw the line. I see them as equal. And we use hierarchical labels when we're doing it in a hierarchical sheet to make that block diagram. That's relatively new for us. We don't usually do that. That was one of the very first designs where I pushed the poor undergraduates to do that. And it worked out really well, I thought. I don't actually care. In fact, if it were up to me, the hierarchical labels and the global labels would be almost indistinguishable because it doesn't really matter. They're still all connected. I know that they have different properties because you can wire up the hierarchical labels differently than the global labels. But as a schematic reader, I don't care, I think is the right way.
I think I'm next. Are you familiar with the post on the Stack Overflow EE forum titled Rules and Guidelines for Drawing Good Schematics? It's by a relatively high poster named Olin Lanthrop.
Huh. Sorry, it's a Stack Overflow?
Yeah, it's on the EE section of Stack Overflow. It's Rules and Guidelines for Drawing Good Schematics. And I like it because it mostly agrees with me.
That's great. No, I've done lots of searches, and I have no idea how I did not hit this. So yeah, that's great.
Okay, just a quick question for when you import symbols, either from whatever library you're using or from whatever website you might be using, to reflect an easier to read symbol. while still, like, I guess, being true to the component package, do you tend to go in and edit the library symbol and then hide all the excess pins and then, but still make them, I guess, connected? So like, I know sometimes I'll make them all the same pin number, even though they're representative of multiple pins on the package, but they're just one on the symbol. What do you usually do to kind of make it look nicer?
It depends. I think that Jason said it best, which is that if you're doing something safety critical, then it's really good to actually display all those things. If you're doing something like us, for the love of God, hide it. And then just keep poking the up button on the feature request for the Dan KiCad guys who have not implemented that yet. Dan KiCad guys.
It's coming.
I bet.
Hey, okay, so I go back and forth all the time with do I make this microprocessor look like the package, or do I make it kind of grouped, right?
Yeah.
And the reason I go back and forth is because I want things to be really easy to troubleshoot on the
Yes.
bench. And, you know, if you have that visual representation of the package, then it's a little bit easier to troubleshoot. So like and I do go back and forth depending upon what I'm doing. It's you know, kind of sporadic like that. But
So
what do you think about that?
This is great. This is great. I have like 100,000 KiCad things open. Let me see.
So while I was looking, what I do for that is I take a screen grab of the pinout from the data sheet and post it in as an image next to the microprocessor.
So here's why I think that doesn't matter. And I think that you're actually shooting yourself in the foot. And the reason why this is not a good example, hold on, I know I have one in here that's RCS. Okay, all right, fine. I'm okay with that. Oh God, now I have to go back to where I was. Nope.
Especially on quad packages too, it's hard.
Yeah. Oh God, now you got me all screwed up. Okay, screw you. I'm gonna do this. Okay, so here's why. When you're doing the schematic, what matters is the actual. Does anybody else hear that siren, by the way?
Yeah, it's another building over.
Okay. When you attach them, you only care about the actual functionality of the schematic. You care that this pin goes to this transistor, right? And in KiCad, when we're debugging a system, I'm going to do this. I'm going to hit tilde, right? And then I'm going to Alt-Tab over to here, and it's going to show me where that circuit is. And so I don't actually care. Right? This is not useful to me because my actual layout is going to be much different than that. And what I care about here is the electrical rules and the electrical connections. And so I encourage you to not do that. And what you'll start to find is you start to use the layout to probe the layout. And you use the schematic just to understand what's going on electrically. And then it doesn't matter anymore. Like, it's just so easy to go back and forth. This actually doesn't help you. It may help you debug when something goes wrong, but it's much more likely for you to screw up a connection when you're doing that package thing. And so we're trying to get the best of both worlds, understanding the connections in the schematic versus the layout and the flow on the board. I hope that was helpful. Yeah.
So I'll add a few things that I like to do. I think one is, it's funny that this is coming up for the second time today, harness your inner Ben Franklin, everything in moderation, including your moderation, right? So you want to like rigidly follow rules until it just utterly doesn't make any sense.
Right.
And so to that extent, when I think of these things, when I write code, I leave books in there to explain what's going on. When I make my schematics, I leave all kinds of comments all over there. And I'm not doing it for someone else. I'm doing it because I will look at it at some point in the distant future and not remember any of it. Last week, I looked at some code that I wrote a year ago, and I've had the same response that I've had when looking at other people's stuff, where I went, oh my God, what crap, right? And immediately found 3 bugs and removed about 100 lines of code by rewriting it. And so to that extent, when I drop down resistors and capacitors, I don't just say, oh, it's 10K. I say it's 10K, it's 5%, It's got this much power before it's going to go up in smoke. And this is its package, which is super important when you got your scope in your hand, your scope probe in your hand, and you're looking at your circuit board. Am I looking for an 0201? Am I looking for an 0402? Now, again, my Ben Franklin, I don't really necessarily do that on a microprocessor, right? I know exactly where I'm going to find that one. But for discretes, inductors, capacitors, diodes, I do 11 by 17. And then if I print it out, it comes out on 8.5 by 11, whatever.
Yeah.
But at some point, you're sitting there and you want to find these parts right away. And the more you put down on there, the more you're going to know why you picked it to start with 2 years ago when you made that board. And so I've certainly caught myself putting down a power level for a resistor and then putting the package on and realizing that package can't possibly dissipate that much power. And you catch it immediately. So that's my 2 cents.
I can't believe I did not put a note about putting standard parts on every sheet, right? That I missed that, and I'm really glad you said something, because you should absolutely have this, right? So that you know what, if you don't make a note, you know what you're dealing with.
Oh, I just wanted to add there are some. Oh, okay. Some exceptions. The feedback pin on a switcher, I've never seen anyone's symbol put it on the left, even though it is technically an input. It's always on the right in every data sheet.
But that's okay. That's right. That's absolutely okay. That's like, so when we say inputs on the left, outputs on the right, that's still technically part of the output circuit, right? Because it is the feedback from the output to the switcher.
Input. I've done it both ways.
It is. And so, again, in moderation, right? Like the flow of that circuit is inputs on the left with all the enables and slow start and all that stuff over here, and then all the output crap and stages on the right, right? So yeah, I don't think that's wrong. Yeah.
One other thing I like to do is sense wires, have them at 45 degrees at the point of contact at where they actually sense the voltage. Makes it look kind of like a
sense wire.
Yeah.
That's good.
Can we go back and look at your Tektronix 422 schematic for a minute?
Yes, we can.
Okay, 0 volts and ground are not the same net.
We have a earth ground there. I don't see another ground. Do you see another ground?
No, but you were commenting, I think, about the 0 volts coming in on the left, right?
It's probably a star ground on the power supply side.
That's not ground.
One of them's down, one in the middle. One of them's chassis.
So this is quite
okay. Thank you. Yeah. Okay.
It's quite common in old schematics, and I'm troubleshooting an old Tektronix optical intensity meter right now, and I measure different biases to different grounds in the system.
So if that's not ground at 0 volts, that's just a 0 volt line.
It's a circuit ground, circuit reference 0, back to the power supply.
Which is different from ground. How?
It could be different from the chassis ground.
Well, of course. Yes. Yeah. That's fine.
But it's not ground.
So you and I disagree on ground, because I say ground.
It's the ground reference for the power supply.
Right. Well, there's the ground reference for the power supply. Then there's the ground reference for my circuit. That's the ground reference for my circuit. So I claim I could take that, and then I could have the ground reference for that, which would be GND or not power supply ground, right? So yeah, I might disagree with you slightly, but that's a beautiful disagreement, not a terrible disagreement.
No, but I agree with you that they drew a lot better schematics.
Yeah.
Okay, well, one last question here.
Yep.
Just a couple more suggestions, I guess. Art of Electronics has an appendix on drawing good schematics that's pretty in line with what you've said. You could
really?
add that as another reference. I'm bringing this one up because you didn't do it in your schematics, and I think you should.
Yep. Good.
Symbols should have a colored background. They shouldn't be a transparent background.
Yes, they should. What?
You pulled up at least 2 schematics.
Okay, but they were undergraduate schematics. Yeah, they were okay. All of my schematics have yellow blocks in them. Yeah, no, that's great. I love that. Great, thank you guys.
Okay. Thank you very much. I saw that there were a couple more suggestions. Please go to the QR code that was shown earlier. We'll show it one more time here. And drop some suggestions in. Yes, and thank you again, Andrew. Excellent.